Welcome back, everyone. And today we're back and we're going to switch gears and go back to voxels. So today we're going to talk about rate casting into a voxel chunk. And the whole idea of rate casting to a voxel chunk is that you want to be able to find which voxel or which subcube in your chunk that you selected with your mouse. So what we're going to use is the fast Voxel Traversal algorithm. It's a very old article. I've read this thing so many times, especially this section that describes how to do how some of the math is implemented. And this is the only set of code they give you. This part's kind of hard to understand for me because I'm not a mathematician, I guess. I implemented the math wrong, but luckily. There was a nice article, another old article from Flipcode, and they kind of explain it a little bit. They do a pretty decent job of explaining it. They kind of just verbatim kind of explain the exact same thing that's in the PDF. But this little GIF really kind of helped understand that I was doing the math wrong a little bit. And they also have some sample code that in C++ that I looked at and I was able to kind of decode it. I did look at a bunch of JavaScript implementations of it, and none of those actually worked. I was kind of hoping to work off something that's array in JavaScript, but I had to go and build something myself. So that's why I spent a lot of time reading this PDF and trying to find an understanding of how to apply the math. Like I said, this section was a little difficult. But so far, I managed to get a really good working version of the algorithm in JavaScript. So let's quickly go look at some changes we had to do the fungi to make this all happen. So one quick change we did is I did in Visual Debugger the ability to visually see just cubes. So you just pass in the minimum and maximum bounds, and this thing just generates a bunch of lines that creates a cube for us. So this way we can debug and make sure the vectors or our array is actually hitting the cubes that makes sense. I see in other algorithms that was using this visualizer to do it, and I wonder if that's where the problem is. Maybe it didn't have a way to visualize it. But like I said, it would visual debugging. Some have a visual debugging really helps a lot. Did some vec3 changes, just a new function called near zero. I couldn't come up with a better name. During the math, I noticed there's some glitches here and there when reaching a value close to zero. When you do division, sometimes you can go to zero, like infinity, and never reach zero. And that will cause me some issues doing the math in this thing. So I came up with a nice solution of just making a function called near zero, and it just checks every component if it's less than this specific value, which is 1/8 minus 6. You could write it either form. I just wrote that because it's shorter. And if it's less than or equal that value, it just automatically set it to 0. So this way, instead of going infinitely to 0, at some point we have to say, we give up. We need a 0 here. So this value works out really well for the voxel traversals. There's a bunch of small changes to our raycast object. One thing is really to what does this one does? Oh yeah, the ability to put in a starting and end position, because we didn't have that in the beginning. So this way I can instead of constantly using the mouse to shoot array, I want to be able to just pass in 2 coordinates, like the starting and ending position, and just be able to refresh the page. So like I said, this thing helps with more debugging, and we can end up using this now with just 2 points. This is a regular raycast without the need of a mouse. And then also fixed up in AAB to keep track of axis. So this way we know which axis and which direction the final intersection point in our box is. So this way, when it comes to voxels, especially what I needed to do is that I need to be able to find which cube in the chunk has been selected, which face was selected, because at that point, when I know which face and which the normal direction is, I can then do kind of an extrude because I want to, like I said, I want to make a level editor and for Portal 2, and I need to be able to do that. So this now tracks axes, basically which axis the raycast is happening. Very simple, and there was also an issue where it wasn't initializing world bounds, so I just add a little bit of here and there. And the last thing was in our Voxel.js, I added get max bound and get cell bound. So this way I know what is the starting or minimum and maximum points for a specific voxel. So this way I can then draw it on screen. Because like I said, it's really mainly for visual debugger to help me just visually draw where that cube is. And it could be used for other things, for rendering other like selectable cubes or whatever else. So with that out of the way, like I said, you can, the code's on the screen long enough for you guys to maybe just type it out if you need it. Else just go to GitHub and just get it as one whole thing. Like I don't know how the viewers are doing. I don't know if they're just following along and typing or just not bothering. So now I'm just going to start looking at some code. So we're going to start off with the usual kind of template, using a regular shader. And now we're going to call in array. In case you didn't know, we're bringing in raycast module and our voxel module, and then a math vox as well, because we need to do vec3 stuff. So I have a bunch of different positions, because every time I did once the code produced the right path, I would click around and then see there was an error. So then I had to go and get those coordinate points and work on the math again, make sure, and then once I get that working, I make sure it works for those two samples. So the current version I have works with all these samples, and produces a pretty good path through the voxel chunk. You'll see in a bit. But that's one thing you really should do, is just keep testing, and trying to break everything you do to help improve your product. Because trust me, it took me days, a lot of nights to get the math just right. And thankfully for that one site from Flipcode or something, I forget, I was able to find where the mistakes I was making in math. I was making a misinterpretation from the PDF file. So let's see. So we're going to start off. So we're going to create an array, and we're just going to debug our array so we can see the array. We're going to make our voxel chunk. We're going to make a very simple voxel, which is 2 by 2 by 2, and we're going to create an ABB access align bounding box based on the size of our chunk. And then what's it, debug? And this one just creates the bounding box of the entire chunk. It makes a debug box of our entire voxel chunk. And then there's 3 versions of the raycast, and I'll explain later why there's 3 versions. But we're going to start messing around with Voxel Rate test. This is really the main function I started with to really put it together. There's some changes to camera, but why not show it really quick? It's just when I run a click, it just grabs an array from the mouse and kind of starts up a lot of what's up here. But this is based on mouse clicking. So once I was satisfied with these things, I would start clicking around and testing more voxels. So basically, you end up doing a reset with all the debug information, and then you kind of just start it all up again. So that's the only change I did to the camera on mouse down. So we're going to start with Voxel Rate test. So we're going to pass an array. So we know the starting and end position of our array and its direction and everything else. And we're going to pass in our chunk. So this way you can use it to grab information for all our voxels, and our bounding box for the overall chunk. So first thing we're going to do is use our array information and do an AABB test. So we're going to test the collision from array to ABB. And if there is no collision, there's no intersection at all. So that means the array did not touch at all the cube. So if I go back to the page, here's the default. If I click refresh, oops, and I can click around. If I click out, and there's an array, and it says no intersection. So if you've seen my video about ray to bounding box intersection, this is just a kind of a continuation of this, because now that we know how to do ABB testing with the raycast, now we're just going to end up dividing that up a little bit inside, but it's done a very different way by using that old algorithm that I found. So that's what we have so far. So we're just going to take a little step further, and we're going to display the starting and ending position of our array. So very easy to, we create a couple new vector 3s, and we just ask to get the position of the array at tbox min and tbox max. T stands for time, usually. And so the minimum is the point that intersects the cube, and max is the point that exits the cube. And then, so once we have those 2 points saved in ray start and ray end, we then visualize it. So if I click refresh, there you go. Black points to the coming in, and gray coming out. So if I click again, so this is all kind of like a quick refresher of our bounding box ray intersection stuff. This is kind of where we left off, basically, from that video specifically. Right? So for testing for voxel chunks, this is what we're going to do first. We're going to do AAB testing. Obviously, that's not in the PDF, I don't believe, at all, because it doesn't really talk about that kind of thing. But I need to know the intersection point. I need to know the starting point, because that helps. Because the PDF file does mention that if you're testing from outside the cube, you need to figure out where it intersects. It doesn't explain to you how you do it. Maybe at the time ABB didn't exist back then, because I think this PDF file was written back in '87. I think this is pretty old. I think it's from '87. I don't think this thing mentions it. Let's not waste too much time on that. So other than that, we need to figure out the starting and end position. So, and that, like I said, we've done that before. All right. So now the next thing we need to do is we need to figure out which voxel in our chunk did we hit. So we know where we hit. We were right here. But what let me refresh. So it's right there, right? That's the point in the chunk we hit. But what voxel did we touch? So we got to figure out which voxel we're touching. And a simple solution, and one of the reasons why I had a lot of problems with my math is because every example I found online, their example is slimmed down because every voxel is a size of 1. My voxels are variable size. They're not a unit size of 1. So my voxels right now are actually 0.2. They're a fraction of a 1. So we need to be able to divide and floor, very important, the start position. So we have x. So let's say the x equals 2.2. Or let's say 0.25, right? Let's say it's 2.5, right? So the x position is 2.5. Or actually, no, for this example, it would be, yeah, it'd be 2.5. Okay, so we divide that by the size of our chunk, or basically the scale of our chunk, which would be is like every voxel is 0.02. No, 0.2. So that equals, I think that's like what, 1.5. Yeah, no, it's not 1.5. It's 1 something, 1 point something. So when you divide it up, it equals to 1 and some value. I think I don't know why I say 0.5, but it's, is it? No, it's let's see, 2 divided by 2 equals 2. I think it's 2.5. I suck at doing math in my head. I know 5 divided by 2 is 2.5. It's like half. So, okay. So our x position is 0.25. That's where the rate intersects, and our voxel sizes are 0.2. So we can use the grid, because the grid, like I said, the grid is also in the same size. This will be 0, x. Like if we're doing x coordinates, this would be 0, that would be 1. 0 and 1. So we know we need this to be 1, right? So if this is, this cube starts at 0.2. Here starts at 0, starts at 0.2, and this ends at 0.4. Very important. This is also important because when we're dealing with calculations, we need to know bounding, the bounding plane that you hit. But that I'll explain further later. But okay, but like I said, if I could zoom in more so you guys get a better idea. So let's say that's 2.5, and this line is 0.2. 0.25, and this is 0.2. So when we divide, we know it's 1, 0.25. But at the same time, we know that this is voxel 1, because this is voxel 0 on the x plane, and that's also 0. But this coordinate for this cube at that dimension is 1 for x, 1 for y, because it's the second level, so the first level is 0, and then it's z is also 1, because up here is the starting point, 0, and then 1. So the coordinate we're actually hitting is 1, 1, 1. And you end up doing that for every single axis. You do the math. So by that alone, we see that the size of the chunk is 0.2, and the x position of our intersection is at 0.25, and we divide by 1. So we got that, and then all we got to do is floor it, and flooring it removes the fraction. Done. That goes away. So that means now it knows that we're in coordinate 1, and that's how easy it's kind of easy to convert these kind of world space coordinates into our voxel coordinates, because that's essentially what we're doing. And that's kind of the very important aspect of this algorithm. This algorithm needs to be does all the math based on addition on integer values. So everything that we have has to be converted into, let's say, voxel coordinates. So that's what we're calling it, voxel coordinate. They're integer values of how we access a voxel. So once we know the voxel coordinate that we're in, we can then pull some information out. So we're going to tell Chunk, get me this voxel, right? So if I take this file or this line, put it here. So I'm going to say, Chunk, give me this voxel. Give me the coordinates, which should be 1, 1, 1. And actually should be right here. And if that exists, draw it, because I'm getting the bounds, the starting, the minimum and maximum vertice to make that cube. So now we'll refresh. Now we're finally debugging. We found the quad, or we found the voxel. So a little bit of so you use these coordinates based on the size. And that's why I said in a lot of examples online, everything is built off the unit of 1. And in my case, I don't want it to be unit of 1. I want it to be variable. I want my voxel systems to be any size I need it to be. So all the math, or like this version of the algorithm I'm using, kind of uses a more variable size of voxels. So that's why it's might end up being a little bit more complicated. It might look differently than if you find other examples. And that's one of the reasons why I'm having problems at the very beginning using other people's samples, because the math is not set up for this, for my way of handling voxels. There's no right and wrong way. It's just what you need, basically. So since I want variabled, I got to live with the extra pains of trying to figure things out since I'm going against the grain a little bit. So there we go. We got, and by the way, all the math that I have will work with the unit of 1. But if you divide by 1, it's a waste of time. So like I said, if you don't need it, you might have to change a little bit. But it will work with any size, including 1. Okay, so there we go. We found the voxel. That's the voxel we want. That's the voxel we hit. That's the starting voxel. All right. So since we also have the end position, we do the exact same thing, and we use also have min and use the max. So just in case the math comes out wrong, because in the beginning I was, like I said, I had a lot of problems with math, and I was using this. I think at this point I might not need math.min anymore, because the problem was that near 0 issue I was having, which this kind of helped fix a little bit some of the problems. But like I said, but whatever, I'll leave it in there because there's nothing wrong with it. Just in case the math somehow gets a little goofy, I want to make sure that I don't go over the maximum value of our voxel cube. So it's kind of just making sure no math errors happen. So we repeat the same thing for our exit point, the gray point in our cube. So once we refresh, now we know the voxel that we came in, and we know which voxel we came out of. Now, this point is not really needed for our voxel traversals, but it's just here for debugging, really. And simply because if you're traversing, the real intersection point is right here. Right here. Because this is where the line actually enters this voxel. That's what the most important thing is, that wherever this line enters a new voxel, that is the point of intersection that matters. The PDF file does not have that information. I had to kind of figure that one out on my own too. But again, this is a complete example of how to do this. All right, so we got the starting. So we're visualizing. We're trying to I'm kind of going through the steps of how I put this together a little bit, to like how I I write everything, then I visualize every piece of information so I can get an idea of how everything's working. Especially if you're dealing with a lot of math and it's related to visual things. Like I'm a very visual guy. So and I want to be a graphics programmer. So why not make it visual? So here we go. So we know this. So now we know our voxels. Okay. So now we need to start traversing it. Like we know that we need to get to here to there. We need to go this way. We need to go this way. Then we need to go down, and then we go that way. So there's 2 more voxels that we need to figure out to reach the end of our chunk. So now we're going to start dealing with some things. So a lot of comments. So you guys are going to have lots of comments. Do you know how many source code samples of these I found that have 0 comments? So I had no understanding, and the variable names are horrible. So understanding everyone's interpretation of the algorithm was a nightmare. So like this whole point of this series to kind of make sure the information's there, like the commented code, very important, especially when you're dealing with tons of math. So bear with me if you don't like all this commenting, but like I said, it's very important, especially for anyone who's trying to find and understand this stuff. So first order of business, we need to know what direction the line is going. So we know the direction from our array, and our array produces the direction vector for us. So if x is greater than 0, that means we're going in a positive way. So we save 1. If it's not, we know it's negative. Then we do a double check to make sure, is it less than 0? We're going in a negative direction. If we're not going in negative or positive direction, then we're going to 0. A lot of samples don't do this. They just say -1 or 1. If for some reason x is 0, it's going to be, it's going to be like an unknown. You might end up accidentally going in a direction that you shouldn't be going, because if for some reason or somehow a direction is 0, you should not be moving anywhere. So that's one glaring issue I saw before. So that's kind of important. I think there's only one example I found online that actually double checked for 0. Or for all you know what, sometimes C++ initiates, I think, to 0, so they don't have to do that. So maybe that's why I didn't notice it. For JavaScript, variables don't automatically initialize to 0, because these aren't numeric value variables. We don't have types in JavaScript. So I think for JavaScript, we need to really be mindful to that, because there's no default of 0. So we need to fill in 0 when it's appropriate. Now the next part is one of the things I made the mistake in, because I had a hard time understanding the bounds, and that's what that one article from Flipboard showed. That made a great sample. So what's happening here is that now we know which direction we're going. We need to find what line in the grid does the ray hit first on each axis. And let me visualize it first. Like both have a good example of it, but I think he has the best example of it right here. Let me see if I could zoom in. So we have array, right? And it's maximum x, or no, actually, this says t max x, but I use it called bounds. Like this is not the same thing as in the code here. This is not. But I'm illustrating it, but it's not tx. But it's the same idea. So, like I said, here's our point of intersection, right there. There's a point of intersection. Oops, wrong one. We need to find where it bounds. Why I call it a bounds is because you have these lines. These are the bounding lines that kind of divide our chunk into voxels, into basically a 3D grid. So as the line's going through, let's say if I want to say what is the next, like, okay, it enters here. From this point on, where's the first spot that X hits? The first bound line, the X hits. So if you're going through here, it leaves voxel that we started in and goes into the next voxel. So that's where it first hits X, the first X boundary. It doesn't hit here, it doesn't hit this boundary, it doesn't hit this boundary, it hits this boundary, but it hits X at that point. So I'm actually have to figure out once you know, you have to find out the value of that boundary. For my example anyway. I need to find where in the world is this boundary. So basically it's kind of like going from here. This is really what, because you end up finding the value from here to here to actually calculate the length that we need for traversal. This is delta, in my opinion. I think that's delta. But okay, so that's what we're trying to do. We're trying to find the boundaries. And the next one is y. So if this is, technically this is z for us. So this is z1, this is z2, and this is z3. This is x0, x1, and x2. So if this line was going in this direction, the closest boundary would be z line 2. Or in this case, since it's going in this direction, is z line 1. And that's why it's important to know which direction we're going. See, that's why we're saying which direction are we going? Right? So let's see. If x is greater than 0, we're going to take the I point, which is the I coordinate for x, plus 1. And if it's not, we're going to use the I coordinate that exists. So like an example of x, This is 0, this is 1, this is 2. This is voxel 1 on the x-plane. So if I am going in this direction, I'm just going to use ix. If I'm going in this direction, if the ray is going in this direction, I want to use ix plus 1 because this is the boundary I'm hitting. I'm hitting the next boundary over. So this boundary 0 corresponds to this voxel 0. This boundary 1 corresponds to this voxel 1. And this boundary 2 has no voxel because it's the end of the... But we still need to know the boundary because that's the direction we're going. If anything, that means we're going to hit this cube at some other point. So once I know which line I hit, let me go back to here. So now I know which line I hit. So like, let's say I hit this line, and that is 1. So I say 1 times cell. So this way I know the distance, this coordinate line is from the origin on the x-plane. So that's the first step. We need to determine the bounding direction, or like all the bounding for every axis. And then we visualize it so we kind of know where it is. So if we refresh, I marked it as green. Green is the idea is that point in 3D space is what describes all the steps, or like, it's kind of like it's basically the first spot that we exit out the cube. Like, so if we're going to exit out the cube, it's going to be at that Z position, it's got to be at that Y position, and it's going to be at that X position. So that's the position that, or the values of that position. It's not a real position at all. It just represents the value of every exit point for our for this voxel, for each, because we're kind of doing we're doing 3D all in 1D. So all the math is done in 1D. So basically we're breaking our 3D coordinates down into 1D and doing the math that way. So if X is so yeah, that's how we kind of determine where does X get out of. X gets out of 1, and when it comes to Z, it goes to this one. So that line's the Z exit, and this is the exit X, and this is the exit Y. So like I said, that's kind of like the magic thing we're doing. We have to convert everything from 3D to 1D, and I think we've done this with other ray casting as well. So now we know which lines, and we didn't calculate what their position is in real space, in world space. Now we move on to the next step. We need to determine time. At what time that exists. So we take the starting point. So we're going to take that starting point and subtract it by basically the X of that point. So the X of this point minus start, which gives us the distance between here and the edge. So it gives us that distance. And the thing is, since we're going in this direction, our whole axis is from this point to 0, essentially. So it's this whole line, probably hard to tell, but it's like this whole line is basically our new line that we're dealing with on the x-plane. Like if you think about it, the line is really from here to here, because the exit is on that plane of our cube. So, like I said, from here to basically here, if you can kind of visualize it, we're figuring out the time that this exists on this. And I think at this point, so, okay. So yeah, we're trying to convert this distance. like I said, we're trying to create, well, in this example, sorry, I'm tired. In this example, I'm taking the distance, I'm taking this little distance right here and dividing it by our entire X array direction. Which is, yeah, so yeah, that little distance divided by the X direction of this array. And that basically, you basically end up determining the time. It basically gives you what time on this line that you're going to hit this line, that border. So we know that basically where this is, but we want to know where it actually exits out the quad on the X-plane. And we do that for all of it. What this ends up giving us is the time needed to kind of figure out the exit position for every step. So let me refresh. Let me see if I can explain this correctly again. Now that I'm starting to remember how it all works. So we have it. So that we know the time to get to this point on this line. So by that, the math is we're determining on the X-plane at what time do we hit on this line? Do we hit that that border or that boundary? Then on the Y-plane, we're saying at what time during this line do we hit this boundary on the Z-axis when we're doing Z. And the same thing with Y. At what point does this line and that Y position kind of intersect each other? Like, how do they intersect each other in the Y position, just in the Y alone? So we're figuring out the times are all different for each one because each one has a different thing. So that's why it's YT, XT. So it's the time on that line that we finally reach the boundary of that voxel, or not really that voxel. It's the next boundary for each axis. And then the final bit of math is delta, is how much movement do we need to go to reach the next voxel on the X-plane. So it's just X direction. So we know what the cell size is. It's 0.2. And we multiply it by our X direction, which is our X direction is either 1, -1, or 0, 0. So we're trying to move. We're trying to figure out how much movement, which movement do we need to go. Since our ray is going, let's say, -1, going in a negative direction, so we know we need to go 0.2. So if let's say if this is 0.2, right? To get to the next voxel, we need to subtract 0.2. So we got to go here. So it's -0.2. So we're figuring out the movement from essentially here to over here. So we try and figure out that number. Then we divide it by, again, the ray direction, which kind of converts it into like the t. I think the PDF mentions that as next we need to determine the value of t in which the ray crosses the first vertical voxel boundary and store it in variable t max x, which that to me is not. Oh, that's what we did. That's what I'm calling the boundaries. Like I said, t max x doesn't make sense to me because it's not. I'm not using it as t values. I'm using it as boundary. Am I confusing myself? This is t max, really. Boundaries I need to figure out t max, and then now we're dealing with delta. And delta is like this is the part we're doing now. The delta indicates how far along the ray we must move in units of t. And this is something that screwed me up because I didn't understand that part. Units of t. So let's look at it one more time. How far we need to move in units of t for the horizon component of such movement to equal the width of a voxel. All right, so that part, the one I think was this was like one of the main part that really screwed me up. This is how much. I think I wasn't adding direction. I think that's what screwed me up. I wasn't adding direction because it doesn't mention direction. That's the size of the voxel, the width of a voxel, essentially. And we need to move it by units of t. That's really the normal vector of array. So that's like, this document's a pain in the ass. Like I said, I'm not a mathematician, so it's kind of hard to understand. But that's what it really means. So we need to divide the size of our cell by each increment, like the actual normal of our direction, and we multiply that by direction, because let's say we need to go. So for the first step, we need to go negative x, because that's the next voxel over. The next voxel over is 0.2 units away. It's the next voxel over. But in terms of this line, I need to do it in units of x normal, basically. So for every step I take, I go from this point to this point, because that's the next step, essentially, because that's the next x position, the next x boundary this ray hits. This ray only hits two x boundaries. It's this one and that one. So that's what it means by, moving units of voxel, by units of t. So that's the first unit and that's the second unit. So that's like the secret sauce, essentially, for that algorithm. And like I said, I had the hardest time understanding it until I found a sample. It didn't have comments, but I saw what I was doing wrong. I saw this, and I was like, oh, it's dividing by that? I was using a different value for division, I think, too. So this whole thing was killing me. And then you have out. Which I don't think the PDF explains it, but it does use it. Like, it does have out. I don't think it explains it, though. But out is essentially, what is the voxel we need? What voxel coordinate means we're done. So if our voxel coordinate starts at 0, so if we reach a voxel coordinate of -1, we're done. That's out. We're out. If we're going in the positive direction, it'll be x length, and our voxels has two values. We have the voxel size and voxel length and the voxel max. Max is essentially length minus 1. So let's say we have, what's the length of a voxel? Well, it's 2 cubes worth. But if you're dealing with like increments of, like, if you're dealing with an array, arrays don't start at 1. It starts at 0. So that's what x max is. It's what's the maximum index that we have. So I probably should change the comments here to describe it better. But so we're saying the maximum. We're using the maximum value, because if the maximum index of x is 1, that's what this value is. The length is 2, so it stops at 1, length of 2, which is basically the same idea as dealing with like arrays, like I said. So if we ever hit so if we hit -1, or we went 1 over the actual index number, that means we're done. That's all over with. And I guess let's refresh and just see what the results of our t's and our deltas are. So there's our t's. Those are the time on the line that we each point, and delta is the steps we take, which is also in t form. It's the steps in t form. So when we hit x, we're going to add that stepping point to here. And now we're going to the final aspect of the algorithm. Boy, this video is going to be super long. And now the entire gist of this algorithm now is to traverse it based on which axis of t, which t axis, I don't know, I feel like I'm saying it wrong, is the smallest. So in this, if you look at this array, this is all our t values, right? The smallest value is x. This is the smallest value. So that means in the first iteration, we're going to move x. So we're going to go that way, which is correct. And then we add that distance time, which that distance gives us the t value to here. So that means from here to here. And when you add it up together, it ends up making a value called like I don't know, over 45. 9 plus 5 is 14, 55? Whatever. No, it's not 55. I give up. Like I said, I'm tired. Long work day. So, okay, whatever. It becomes a much bigger number that these are. It goes in the 40s. All right, let's just say that. So the second time around, the next number that's smallest is this one, and that's the y-plane. So that means we're going to, and we know which direction we're going negative. So now that we're in this cube, we're going to go to that cube. And then the next loop, we add 43 to it. Now that's another big number. That's going to be in the 60s, 67. So this one is the 40s, that's 67 and 29. So that's the smallest number, the third loop in. Now we're going to go in the z position. So once we're in this voxel, we move over, and that's our exit voxel. We're done. Because then the next step we take, we're going to hit a boundary of -1, and that means we're done. We're out. You want to keep going until you're out of bounds, and then you know you've reached the final voxel. And let me comment a lot of this stuff out for now, because we don't need to do that. Oh, this is something else. This is extra credit for that algorithm. This is the stuff that's not in the PDF. So the part that's not commented out, and you have the if statement, which is in the there's a 2D version and there's a 3D version. So the 3D version is like 2 if statements, but apparently but you can optimize it into 3 ifs. So if x is less than y and x is less than z, this is what we do. If y is less than z, we do that. Else, we're going to do z. So the first thing we're going to do is we're going to move. If x is the smallest axis that we're moving, we take x direction. So we use x direction to move our index. So this is our index. So we're going to move to the next voxel. So if I know that's voxel 1 on the x coordinate, I'm going -1, so it's going to be 1 minus 1. So now we're going to be x coordinate of 0. So now I know what the index of the next voxel that we're moving to. Check to see if we're out of bounds. We're not out of bounds. We're good. Then we add to the t value, or a delta, and basically we're output. And we repeat that process for every axis. So at the end of this loop, we can see the information, and then we say, okay, well, I have this new ix Give me the cell bound for that one. If it's not, there's no problems, I write a debug. Do I have that? So that is essentially near the end of the default algorithm that you'll find from the PDF. And when all said and done, that's what it does. And you can kind of see the information as we traverse through. So, we move X. So now remember, this entry voxel, the black one, is 111. So the first loop, we move to 011, which is this one right here. On the next loop, we moved the Y position. So now we're down this voxel. And then at the very end, 00, and that's our exit. After that, we're all done. And that is really the algorithm as a whole. But now we need more things because we're dealing with voxels in terms of making an editor. So we need to know at one point we intersect each voxel. And we do that the same way. Here, this is the section that handles it. Again, we have to calculate the index of X, and based on direction, because we need to figure out which bounding thing we're doing. And it's, like I said, it's the exact same code that we figured out IX to begin with. So it's pretty much a repeat of the code. We're figuring out that we know the IX. This creates the coordinates, like the world space coordinates for the boundary we're moving in. So I'm trying to get that point right here. This boundary, that plane essentially, or just that face. I'm trying to get the point on that face. So I need to know where that axis exists, and it's, so I know it's the coordinate is I, so we know it's 1. So we know it's 1. So 1 times cell, that's 0.2. So that's 0.2. So we take 0.2 and we subtract it from the origin X, from the starting point of the array, which creates a nice length, right? And then we divide it up by our vector length, the length of the entire array, because the one whole unit is the entire length of the array. The original, here's an equation that is original for finding t on a line. So it's the vector length times t. The vector length is, yes, the vector length times t. So it's like the whole length of the array. We want a fraction of it plus origin equals the position. And the thing is, we don't know what t is, but we know what our vector length is, and we know what its origin. So when we move the equations around, the first thing you do, so we know what our position is. So we calculated our position in an x-plane, right? So we know position, and we know origin, and we know vector length. So we say, well, we have position minus origin, because we're writing the equation, and all that's left is vec line and t. But we need, t is the unknown, so since this is the multiplication, we divide by vector length. And that's how I determine the new t value, by rewriting this original equation of how to get a position on an array. Yeah, so it's just algebra, just rewriting equations based on the missing information you don't have. So now that we solved t, we then could go to the array and tell us what t is. And what t does, what get position is this exact equation. It because like I said, it knows its vector length, it knows its origin, and we just fill in t, and that's what we passed in. So it's get pose is actually this equation, and we did it in reverse to figure out t, that we can then use it. And there's no comment here, or not comment, semicolon. So once we know, like at the T position at that axis, we say, well, give me the full position, the X, Y, Z of that. And at that point, we can then draw the point. All right. So if I click refresh, in blue, you see the point of intersection. You find both points of intersection that the line goes through for each voxel. So now we know where we hit each voxel. And the last thing is we know which direction did we go. And to determine direction is, well, we know we're going in the X, we know we're going in the X direction. And what we have to do is go the opposite of wherever we're going. So if I know I'm moving in an X direction in a negative way, so I'm going that way. So that means the normal direction is that way. So figuring out the normal is really just negative XD direction. Because if that direction is negative, it becomes a positive. It's a positive, it becomes a negative. And all I'm doing right here is really just multiplying that value to make a small number. Because this, like I said, this is a value of 1. So I'm making that into a small number to visualize it. So if I click refresh, now you see the direction that we're moving. So when we go to this voxel, we're hitting it at that point, going in basically that direction. And if I were to uncomment all the code for each one, we'll be golden. Click refresh. So let's see, I don't need this right now. Refresh. Let's get a nice big view of it. And there it is. Like I said, we move this way on X, then we go down on Y. Did I forget to uncomment something? I think I forgot to uncomment Z. Yes, I did. It's like, hey, where's the Z direction? If I click refresh again. There we go. There it is. So now we have every single point that we hit for every single voxel and every direction we hit. And like I said, then it's important to know what the normal direction is. Because let's say I hit this last voxel. Here's the point. Here's the normal direction. That means if I want to, let's say, extrude, that means I want to build a voxel next to the voxel next to it. So this way, if this voxel exists, I'm going to automatically extrude into this zone, this voxel zone. This will be filled in with an actual voxel. Like this is a voxel chunk that's empty. No voxel is filled in. And that is essentially the entire algorithm of how to intersect all the voxels within the array, knowing the points of intersection for each voxel and the normal direction in which of that face directly. So this way you know which face it is. It's easy to tell which face it is. Like if it's on the Z plane, it's 1, then it's this side. If it's negative, it's on this side, essentially. And then you could just keep shooting, and it works really well. It shows you every point, every direction. So it goes this way, goes that way, goes this way, goes that way. Done. And there's that glitch. That glitch right here is that close to 0, which I fixed it in the different version of it. But yeah, there's a little glitch here, but that's because we're using my rate test file function, which doesn't have all the optimization and whatnot. But yeah, there you go. So now you can basically traverse through a voxel, or you can use this as a way to select voxels in a chunk, which we're going to do in later videos. So this is a very long function, but it doesn't need to be that way. I have another function underneath it called Voxel Rate Cast. Voxel Rate Cast is my final version of the function. It's cleaned up. I tried to rewrote some of the comments. I did, and it's written in like over here we have like all these if statements. We have like lots of if not over actually over here. A lot of if statements. Each one of these is an individual if statement. I decided to optimize it. So here we have 3, another 3. Oh, actually, this is more than 3. This is 3. This is 2 in each one. So that's 1, 2. That's 6, 6, 9. So we have like 9 if statements. Excuse me. We have 9 if statements. So I've decided to optimize it and just do 3 if statements, and then just apply the specific. So kind of combining each axis at a time. So we have less if statements in the code. This feels longer, but is more optimized essentially. Like I said, there's less statements. We're not doing a bunch of if statements for every single variable. This could probably be a step further, and if we did everything as vector 3s, we can probably bring this down by quite a lot. It'd be the same thing. Yeah, it'd be still yeah, it'd be the same thing. So we don't have to do that. And I cleaned up. And when we're calculating t, I don't have it in here. Remember, we're calculating t, or xt and delta. We're dividing by rate direct.x. I do an invert and then multiplying, because since we're using it twice, it's I guess cheaper to have one division and one multiplication on the CPU as opposed to 2 divisions. So it's like 1 division. It's better to have 1 division and 2 multiplications instead of 2 divisions. Like, I guess divisions is worse on the CPU. So 1 division, 2 multiplications instead of 2 divisions in general. So I did that little bit of optimization, and then I changed up how to do everything else. And this version also has a lot of display code still. For what you're gonna do, you might not need all this information, because this is kind of a lot of garbage. This is the same if statement, but now it's tracking the axis and normal in a different way. Where originally I had all that code, I'm tracking it in a different manner, and then here I end up calculating the normal and the intersection point, and then you do the final. And this, like I said, this is the more clean-up version and optimized version of our test. This one, like, basically, I would take this and then remove all the visualization, because it still has visualization code, like all the debug lines, if statement, things like that. That's the only thing that needs to be removed. But overall, this is pretty much ready to go, and it has everything that we need. And then I have the mini version, which goes back to doing it this way, but this is clean. To me, this is cleaner, and I wanted to make this a minimum version for people to have as a starting point, as a good example to learn. Like I said, one of the biggest problems I just had no good examples really to learn. Everything was very complicated. Everyone had a use case for their voxel thing. And this function, the minimum function, has no use case whatsoever, other than traversing through the voxel and finding every voxel that you cross, its point of intersection, and well, it doesn't do it for every single one. It only does it exits out the loop. Once you hit the end, it exits out and then tells you the information, which access the final voxel. It only gives you the information of the final voxel, the intersection point, which axis, which direction, the voxel coordinates. It gives you basically just all the information of the last voxel. Because ideally, right here, this part where it says do something with the voxel, this is when you kind of check to see if that voxel's filled in, and then you can kind of exit out. That means, okay, this voxel has been filled in. That means there's an actual collision. We're not doing any. This example, this whole lesson has nothing to do with collisions. And the collision is just to check to see if that voxel exists in the chunk, if it's been filled in. And like I said, this is the bare bones example with lots of comments. I try to write the code as neatly as possible because I really want a sample of this online for anyone who has trouble reading the PDF and looking at other people's code, to have a good example as a starting point to understand it. That's why there's 3 versions of it. This is the version you probably use if you want to actually do something with it. This is the version you use if you just want to learn the algorithm. This is the learning version of the algorithm. And this is just me trying to figure it out on my own. So like I said, this is the algorithm plus other things I added to it. Like I said, the intersection point and the normal face that you hit of the voxel. So you got the complete thing you need to select voxels in a chunk. And this is probably a super long video, and I probably should just end it now. Hope you guys learned. I hope I explained it well enough. I spent many nights figuring this out and racking my head and banging it against the wall. I did start this video when it was light, and now it's dark. Yeah, you probably can't see me right now. Now you probably can because of the white screen. So yeah, that's it. If you have any questions, this was a very complicated, I guess, thing that we put together. But hopefully this sample file with all different versions of the code and then the way to visualize everything can make it easier for you to learn. Like I said, you can see the entire traversal of the voxel. I guess that'll be it. I guess I'll see you guys in the next video, and please like and subscribe. And I'm almost at 1,000 subscribers. That's kind of awesome. So keep on subscribing, guys. See you guys in the next video. Bye.